Fortunately, all the plugs is also off. All the plug is off. The power from the wall. I think the electricity for this, all this power is not working. If you can try, but I think everything, because even the air conditioning, I think is off. No, no, this one. See, number? Hmm. But all this power is not. Is it on? I don't think so. All right. Let me call somebody. Hello, assalamualaikum. How are you, brother? Uh, I want to ask you something. I'm having my lecture in the Kuliah Lugo. But all this projector and power in the wall is off. I don't know who to call for this. Do you know anyone? Power off projector and all the power plug in the wall is not working. I think there is a main switch somewhere who's off. In classroom? Yeah, I tried that. That's off as well. That's not working as well. No, no. The problem is not the projector remote. The power, the electricity is off. even the power to the wall. I want to charge my laptop and it's not working. So I think electrical note. You know anyone? The room numbers. Yeah, the one that's making the room. Uh, you know the Matlab, facility in this building near the front door, making the room. So I tried to call someone in the back of the team. They like the office, it's going the main gate of this building. Get locked the building, and they get we have, but I don't think it's yeah. This one, they use the end of inside the one that is oh, you know, someone will come. So you know the because unfortunately my laptop is also needs some power. For the time being, let's discuss about one case first. I'm going to demonstrate how the two-dot vibration system, which we discussed earlier, by hand, and see how it looks like when we transform everything to Simulink. We take the very same example. This is the first case.
This is K1, K2, K3, M1, and 2. It is degree of real system, undamped, there's no no electricity. Projector and plus there is no power. Plus no electricity. Thank you. So this case is stood up. You don't see any external forces working on it. That's why it's free. You don't see any damping, undamped. So just like any free vibration system, it will not work without initial conditions. So you need initial conditions. What are the initial conditions? So if this is x1 and this is x2, you can have either x1 0 or x2 0 or v1 0. And it depends on what value you want to put it here. But the EOMs, equation of motions, is always going to be M1 x1 double dot plus K1 plus K2 x1 minus K2 x2 equal to 0. This is the first one. And second one is x2 double dot plus K2 plus K3 minus K2 1. I hope this is smoothly flowing when you want to derive the equation. In the beginning, okay, probably you need some free body diagram, but once you do this again and again and again, you get the pattern. So once you want to transform this to Simulink, in Simulink, you want to get first mainly only one term in the left hand side. And this one term is in the left hand side should be the highest. So the first one is going to be x1 double dot equal to so can you turn this on? Okay, I will still I will still turn on my Zoom later on, so you can get the recordings. But you can follow this through the screen. So to do this, I want to move everything except the x1 double dot to the right hand side. So you will have k2 x2 minus k1 plus k2 x1 over, or I want to multiply this by 1 over. Why we want to do this? Because we want to define what is x1 double dot, because later on we can get x1 dot by integrating this, and we can get x1 by double integrating. What x2? x2 will be obtained from other equation. So it will be all interconnected. So the second one is x2 double dot equal to k2 x1 minus k2 plus k3 x2 multiplied by 1 over. Going to share my screen. export this. All right. So I'm going to share my screen. You've done this earlier. You've done this simulation. And we will start with the first term, which is the x1. Okay. What should you start with? Integrator. I'm going to start with 1 over m1. So this is actually the gate. I can say this is the gate. Okay. I'm going to write this as 1 over m1, which in normal situation, you will see an error message, but it's okay because later on, you can solve this by defining what is m1. And second one, I'm going to copy and write the 1 over m. Okay. So now I'm writing this. 1 over m1, 1 over m1, second one, 1 over m2, 1 over m2. What is this going to multiply? This will be multiplied by k2 x2 minus k1 k2 multiplied by x1. Okay. So I need to have the term in math operation, addition, the results of this arithmetic operation will define the k2 x2 and k1 k2 x1. Okay. So this should be the result of k2 x2. So I will put again the gain here. Okay. I'm going to write this as the k2. Again, k2, because we haven't defined what is k2, it will show an error message. Minus I'm going to put this here. I'm going to write k1 plus k2. Okay. And this later on should be the x2. And the second one should be the x1. So what do you have here? You have k2 multiplied by x2. Remember, x2 later on is a variable. You will have k1 plus k2 multiplied by x1. Okay. To zoom in. Okay. And this is actually k2 x2 minus k1 k2 multiplied by x1. What you have here is going to be x1 double dot. So this you will have x1 d dot, which by right, if you want to get the x1 dot, you need to integrate one time. This is going to be the x1 dot, and you integrate again, you get one x1 dot. And this you have x1. Okay. So this is the base form of the equation, except you don't have the variable x2, you don't have the variable x1. Okay. Okay. I'm going to remove this to make it faster. I just want to copy this. Okay. You can do that really fast by blocking and right-click dragging. Okay. You don't need to copy and paste. Well, the thing I need to convert this into 1 over m2. And then this has been changed to x2. This is a label anyway, so it doesn't affect anything. So just to make it easier, it to be x2. This is still k2 anyway, k2 x1. So it should be k2 x1. And but second one is going to be k2 plus k3. X2. Okay. The gain, oh yeah, k2 plus k3. Okay. So the last one is just to connect what is missing. What is missing is this x1. You can connect this one to x1 as well. And then you will connect the x2. And you'll connect the x2 as well. Why do you do this? Why I do this? What do you mean? So we connect the output, this one, to K2. Because to go to this, yeah, to solve this equation, I need two variables, x1 and x2. To solve this one, I need x1 and x2 as well. Where do I get the x1 and x2? From both equations. So that's why these are, if you think about it, these are two-dot system, each having its degree of freedom, but it doesn't mean it's disconnected. It's independently moving, but it's influencing each other. So how do it's influencing each other if all the blocks are disconnected? There has to be some connection somewhere, right? Now it depends which one you want to observe. For example, in normal situation, when you do this, the question will be, roaming around, what is the function of x1, right? It means x1t or x2t. That's why we did all this Laplace transformation. We did the assumption and so on to actually get the function. But once we get the function, what is the goal of that function? You want to see the chart. Because if you have xt equal to 5 sine 5t plus 6 sine 60, it doesn't mean anything. You cannot see it until you plot it in the chart. So this Simulink will help you get the chart right away, depending on what you want to see. Okay. For example, traditionally, you want to see what is the function of x1, what is the function of x2, right? So you can run it, but remember, they still have red in it. So what does it mean? I need to define something. How to define it? The easiest way to define it is by writing it in the workspace. This is the function of the workspace in the right-hand side. Okay. Did I share the whole thing? Okay. This is how can you display the workspace? Actually, by default, you will see the workspace. If not, then you can actually turn on the view. We can show. Okay, this is variable. Is it not appear in your screen, the workspace and everything? It will be there. The workspace. I think it should be there. It's in the main page of the Matlab, not in the Simulink window. Not in the Simulink window, in the main Matlab window. So now you can see that all the variable in the workspace is still empty except for the out. So I want to remove this. So everything in Simulink, if you have a variable, if you have any constant, they will check the library in the workspace. So if it's empty, the red colored message will appear. So we need to make a definition here. What is M1? M1, just like our example earlier, I want to equal to. So you will see it here. M1 is equal to 1. M2, I can write it equal to 1 as well, but I want to write it M2 is equal to M1. It's 1. And then I have the K1 equal to 1 as well. K2 equal to 1. K3 equal to 1. Okay. So now you notice here, we don't really have a unit, right? 1 what? Gram, pound, kilogram, tons. So you have to put a consistency in your mind that whatever you put it here should be in the same level. So to be simple, I like to make everything in SI unit. Or if you want to put in imperial unit, make sure you have a comparable unit. Because Matlab, they don't care about the unit that you put. But you know that in the system of unit, if one is gram, one is kilogram, you cannot mix together. So you have to do your own equivalency conversion. So I'm telling myself this is all in SI. So if M is 1 means 1 kilogram. If K is 1 is 1 Newton per meter. Same thing if I put the C as well later on. Okay. So I'm going to go back to the Simulink. Okay. So now I have put the M1, M2, K1, K2, K3. But if I run it right now, what will happen? Okay. I'm going to show the scope. Okay, this is the scope. When I run this, zero. I don't see anything. Why?
Reduce the scale.
Want to reduce the scale? Define what? No. Unit, MATLAB don't care about the unit. It's SI. So 1 kilogram is K, then Newton per meter. Now, when we run it, both show nothing. You think we made a mistake? We should zoom it, zoom it, zoom it. Nothing. Strange, right? You want to connect both? You want to see what happened if both shown in the same picture? Sure. 1 and 2. Zero. What happened? It says free vibration. We set all the vibration system. We put the mass, we put the K, but there's nothing to make this move, right? Nothing to make this move. So you need to define initial conditions. So what are the initial conditions here? You have two categories for each variable, either displacement or either velocities. So here, this is x1. If you click in the integrator, you have initial conditions here. So if say I will put x1 0, say equal to 0.01, or make it x3. This is for x1. This I'm clicking it here because the output of this is x1, right? So if I double click here, I put the initial conditions. This is the initial condition for x1. So x1 0. What if I want to put the initial velocity? This is the velocity because the output of this is x1 dot. If you double click here, you can put the initial conditions. By default, it's going to be 0. So if everything is 0, you don't have no reason to make this move, right? So let's write again. I have put only the x1 0 initial conditions. I'm going to run it again. What is this? Why it's so something like that? I'm going to make the stop time a little bit longer so you can see probably a bigger picture. This is x1. This is x2. And this is the comparison of x1 and x2. x1 is yellow, x2 is blue. If you want to see, is it true with the legend? Yeah. Yellow is x1, blue is x2. X1 is what? We define the x1 initial condition, x1 0 only. You don't define the x2. If I'm not mistaken, this case previously, so if you see something like this, you know exactly this is not happening in any natural mode. Natural mode means it's moving in sync like this. Okay? So in sync means if the x1 is moving to the left 1 centimeter, at the same time, the x2 is moving to the left 1 centimeter. This is actually the example from the book in chapter 5, in one of the case study about setting the initial condition for each mode. And the answer is if the initial condition is the same for displacement, you will get the first natural mode. So I already changed the x2 initial condition to, sorry, not 1, 0.1, the same like the x2 initial condition, 0.1. Okay, so if you run it, this is x1, this is x2, and this is x1 and x2. Why? Why just blue? The yellow is right behind the blue. So it's happening in synchronized motion. If x1 is moving to the left 1 centimeter, at the same time it's moving like this. So that's why you cannot see the difference. Both are moving exactly in the same synchronized motion. This is natural mode. This is the first mode purely. And what is the omega n? Omega n is purely the first mode, omega n. So first mode, omega n, is, if I'm not mistaken, from your book, is 1 radian per second. 1 radian per second means in 3.14, it's moving in synchronized. So you can actually check. Okay. If I'm not mistaken, check again in your book. So what happened if I'm having it in purely second mode, 100% second mode? In your book, it says that it will be purely in the second mode if the initial condition is in the opposite. So if the first one is 0.1, the second one should be minus 0.1. So I will put the second one minus 0.1. And we'll try to run it. There. The frequency is higher because now it's moving like this. When it's moving like this, it's slower. When it's moving like this, it's faster. Okay. And it's perfect. Okay. Let's see the blue and the yellow. And then, what happened earlier? Earlier, it's not in both situations. Remember, it's going to be purely in one of the modes, only and only if the initial condition is satisfied. So if it's not satisfied, say turning it back to 0, or not just 0, I'm just adjusting that a little bit, 0.15. Slightly adjusted. What will happen is start to see some differences because now it's not 100% in the second mode. Some of the first mode is actually coming to interfere.
It's combination.
It's combination of both. So the more combination you have from both, the more seems it is chaotic motion. This is going back to the original. So this is what happened. So this is the combination of the first and the second mode acting together. So you have distortion in frequency. So the frequency seems not really, if you see the big wave, it seems like the first mode. But if you take the ripple, this is actually the second mode. But you have distortion in the amplitude as well. Okay. This is the very simple case of 2.3 undamped. Okay. What if I'm changing this not to 3, but to 4? I'm giving an F. This can be anything, can be harmonic, which is we've done it by hand. But now, since we have the tool, we can take the F as anything. We can take the F as set, as impulse, as random function, anything. We have the tool. We can have initial condition, but we can remove this as well, because now we have a reason for it to actually move it. By definition, the EOM, because now M1 and X1 is actually experiencing F. And adjusting everything, the F now should appear in here. This is FT minus K2 X2 plus K2 X2 minus. So this actually appears. So adjusting from free vibration to forced vibration, I'm going to put back the initial condition to 0, assuming that we don't have any initial condition. This is also 0. But we need to have something more here. This is minus. This is plus. And this should be the force vibration. Okay. Now, how do we put the force vibration? We have sources here. You can put many different types of signal to simulate the external force. You can have sinusoidal, you can have ramp, you can have step, you can have pulse, anything. Let's start with the sinusoidal wave. Previously, when I give you the extra assessment, some occasion I give you sine, some occasion I give you cos function, right? This is by default is sine. So if you want to change the sine to cos, you have to put the bias. You put the bias, sine will be cos, right? So let's now put this as a normal sine function. For example, the amplitude, and remember, this is F, gentlemen. Means the amplitude of the force is always in the unit of Newton. Okay, this is force. Because Kx is also force. This is force, this is force, this is force. And because everything is force, the sum of all forces, if you balance sum of the forces and you divide by m, you get acceleration. So if you think about it, this is all still makes sense. So remember, whenever you have the force, you will think in the unit of Newton. So if I have a system like this is different. Previously, x1 means I'm shifting the position of m1 1 centimeter to the left or 1 centimeter to the right. That's x. X means displacement. But if you talk about F, talking about force. So if you have sinusoidal force, you actually cannot really predict unless you really calculate the static deflection. But basically what you're doing is you're pushing the mass to the left and to the right harmonically. You don't care actually how far it's moving. You don't really need to know, because what you're doing is you're pushing. And now in this case, if I put the amplitude is 1 and the frequency, I don't want to put 1 radian per second. I want to put maybe something less, 0.5 radian per second. Yeah.
You said the changeable device. What about the phase? We wouldn't say the phase is 0.
Oh, sorry. Sine and cos is through the phase, not through the phase. Bias is actually you're adjusting the 0. Yeah. The sine to cos is actually through the phase angle. So okay. So now I'm pushing left to the right by 1 Newton in the frequency of 0.5 radian per second. Remember, this is in the unit of radian per second. If you have a mindset, the frequency is in hertz, then you have to multiply it by, divide it by 2 pi. All right. Now I'm having this, and I want to run the x1. With 1 Newton, apparently it will move 1 meter. Left, right, 1 meter. And the second one, something like this, and the combination of it, something like that, is almost dominantly first mode. But remember, this is force, vibration. So most of this, the big one that you see, is dictated by the frequency of the excitation. Because remember, in force vibration, you have two different response. One is the transient response, which is like the free. And second one is the force response, which is dictated mainly by the F. This one, I use the F, the frequency is 0.5 radian per second. This is what it looks like, 0.5 radian per second, the big one. As a proof, if I increase this, I will increase probably to 5 radian per second. What you will see is, okay, you will see the 5 radian per second, the small one, this is the 5 radian per second, while the big one, this is the natural frequency. So it's combination of it. And you will see how it looks like when it gets to the resonance, where omega is equal to omega n. If I'm not mistaken, the omega n is 1 radian per second. So let's try. If it's equal to 1 radian per second, this is the resonance. Gets bigger and bigger and bigger and bigger. Even if I prolong the simulation, it will get bigger and bigger and bigger and bigger. Okay. What if I have the other resonance? The other resonance is in the second mode. Okay. The second mode, if I'm mistaken, is square root of 3/2. Can you check in your book, in the example, what is the second natural frequency?
Small change.
Small change initially. Yes. Because the force initially will start the vibration, will start small. The transient response still affecting so much, but if you see, the more it goes, because it gets bigger and bigger and bigger, the transient response will be least affecting. We can see this factor when we start introducing the damping. Okay. You start introducing the damping, then you will see the difference. Square root of? Square root of 3 over m. Yes. Square root of 3 over m. 3k over m. Square root of 3k. 3k k is what? So square root of 3 is what? Square root of 3 of 3. I can put this function as well here, square root of 3. Let's hope this is the right value. Still have the resonance. Because these two frequencies are the frequencies of omega n. So you have, in single degree of freedom, you have one trap only. The trap is only in the omega n, because you have only one omega n. But in 2-dot, you have 2 omega n. So omega n on the first mode and omega n in second. So this is what happened. All right. Now, this is the second one. If I put force, is it possible to put force, but also with initial condition? Yes. In this case, it's going to be much, much easier to put. So 0.1, I'm going to put it back to somewhere more friendly. Let's put it maybe 1.5. So in between first omega n and second one. I'm sorry, this is 1. Oh, sorry, this one is 1. This one is square root of 3. This is frequency I put it wrongly. Farm. Okay, this is the one in the second mode. Yeah, this is more correct. Why? Because now the resonant in the second mode say that you have to get different phase. If the first one is moving to the left, second one is moving to the right. So this is what happened. So this is resonance in the second mode. Anyway, okay. Resonance in the second mode. Okay, now I'm going to change this to somewhat more friendly frequency in between 1 to 1.7. But at the same time, I'm going to put initial conditions. This is what happened. So we have combination between force and initial conditions. So you can put velocity initial conditions as well. Put the second one, say 1. This is what happened. The more variables you put far away from the H mode, the more chaotic it will seems to be. Okay. Now, this is second one. What if? Let's start to put damping. I'm putting the damping in the middle of M1 and M2. I'm just saying this is C. So this is no longer damped, but no longer undamped, but now it's damped. I just have one C in between K1 and K2. What will be the implication of this? M1, X1 double dot, plus K1 plus K2, next one. Which one will change? So, what will be here? That's plus C, X1 dot, minus C, equal to. What about the second one? Will it be affected? Second one will be C plus C X2 dot minus C X1 equals. So here you will have the additional term here. This is FP K2 X2 minus this plus C X2 dot minus C X1 dot 1 over M1. And this one will be plus C X1 dot minus C dot equal to 1 multiplied by 1. Now I will adjust this. I need to have plus and minus in the end. I'm going to adjust a little bit down. And then I need to add the C. There's not really a one way to do this. You can adjust. You can make it C X1 minus X2, and then you can put it here. As long as mathematically correct, it's the same. This is C. Also, this is C. This is going to be C. First one is X2 dot multiplied by x2 dot. Second one is going to be c multiplied by x1 dot. So this one will be here. This is the x1 dot. But this one will be here. I'm not going to be really perfectionist about the neatness of this, but the more and more you have a connection, the more messy it will look like. I have plus and minus as well. And I will put also the C here and the C here. First one is going to be C plus x1 dot, and second one is C minus x2 dot. So I'm going to take it from here. Yeah. And second one, I'm going to take it from x1 dot and take it from here. If you don't follow through from the very beginning and you just see this, it will be very, very difficult to follow because it looks, the more and more you done it, the more and more messy it will look like. Just like when you do wiring. If you follow from the beginning, you know exactly what to connect. But when you just see the final product, it looks really, really messy. So make sure you try to follow through from the beginning. Okay. Now we have the C here. We need to define the C. Yes. We go back to here and we define the C. Now, if I want to make the C tend to be more under that, I need to get significantly smaller C because zeta value is, what is zeta value? C over C critical. What is C critical? 2 square root of mk, right? So if m is 1, k is 1, roughly you can say that C should be, if I put C is equal to 1, should be around 0.5, right? So let's try to make it C equal to 1. So I have only one C anyway. And we'll try to run it. I'm going to remove the messy initial condition. I put the initial condition to 0. This one also, I want to put it to 0. So depending on the situation, but in the case study, I will give you some condition. If there's initial condition, then initial condition is there, but if not, then it's not. This is what happened. Okay. Compared to if I don't have this, if I don't have the C, this is how it looks like when I have the C. Now, this is what it looks like if I don't have the C. Yeah. So what happened? What happened actually? What makes it different? Mm-hmm. Yeah. Why? Yeah. was actually eliminated by the damper. Yeah. If you look at the lesson about the force vibration, the effect of damping is actually eliminating only the transient response. Okay. So you have transient response, you have the force response. So let's take a look at what happened when it goes back to the pre-damp vibration. I'm going to put, this is 1, and this is -1, which is the second mode. And I'm going to put the damper on. I'm going to put the damper again. This is supposedly the 100% second mode, which has constant amplitude. But now, with the second mode, you have something like this. This is supposed to be 100% second mode, where in the beginning, you have something like this. You have opposite. Initially, the x1 is moving at 1, the x2 moving at -1. In the first wave, it will intersect, but then, because of the damping, it's gone. Okay. Now, this is what happened in the transient response. Okay. Now, if I add the sine wave, things going to be a little bit different. This is what happened. You see the transient response only happening at the very beginning. So this is where probably the very first portion is where the transient response is actually kicking in. The one after is purely steady state response, which match to the excitation frequency. Okay, match to the excitation frequency. This is just only if you push in one side. So you can see other combination as well. Now, what actually to do with it? I'm going to give you more real life relevant to that. If you write the problem, each bar supported by spring and again, right? Don't forget, your car is actually, most of the car is using pneumatic wheel. Pneumatic wheel is to higher filled by air. Higher filled by air, basically having springy effect. More and more you put the pressure, the higher the kick. But at the same time, the rubber is also having density. So if you look at this is also a spring and a depth. This also connected. So if you look at this, in one of the simplest representations, you can see the representation of mass of the car, mass of supported by a spring, supported by a damper, and you have the mass of the wheel supported by representation of the K of the wheel, and also the C. So this is the K of the suspension, C of the suspension, K of the tire, C of the tire. And whenever you move on the rough road, you will have variation of displacement from subject. Right? So if I say this is x of the car, this is x of the vehicle, and this is x of the road, you're actually having your freedom. It's actually mimicking the case of this. So if I have something like, what is the equation of motion? What is the yield? First one. And car. X car. Wow. C suspension. X car. Plus A suspension. X car. Equal to 0. Equal to 0. You don't have exam. Oh, maybe okay. Let it be, but now we can find out. Where is it connected? One to the X bar, another one. Minus this bar. X bar minus this X mu. Unless we have working on the this is the first one. Second one. And we'll X mu double dot double X mu plus what? It will minus the function. It will Simulink. And it's the thing, is it 5? Okay, let's go again. If you minus the section, multiply by what? Oh, the same factor. You will plus theta multiplied by x will dot and also a will plus k suspension multiplied by x equal to 0. Minus. See, all with x will is double. X will double dot with mass, X will dot with C sas, C will, X will with C sas and K will is done. But you understand that you still have all of this that's connected to this, all of it that's connected to this, connected to some other variable at the beginning. Minus. Now I have C sas X dot minus C sas X dot minus C sas X minus A mu. This is A C A will X equal to what? Equal to F.
So,
but I think the zero, they have long enough working anywhere. With the same measure, right? What you should have in Simulink. For the first, it should be what is x bar dot and what is x real. What about the extra dot? You don't have the double dot for this, right? This doesn't know man. Second one, this tag and the input of these terminals. Just like the F. So basically, both of this representing the F representation. So F can work directly pushing this pushing this on the other. Or it can be, no, I'm not going to push it. I'm just going to move this a little bit in a measurable statement. And this actually will act as a representation of FP working from what is this FP equal to? FP equal to T will multiplied by the actual of the root. And also K will multiplied by the root. The higher the K, the higher the F, the higher the C, the higher the F. The softer the K, even if you put not really in the center. It's right now. What happened with it? It should be start with 1 over m half and 1 over m v multiplied by something. And then you can work on it. Let's try and try to work on in Matlab. I'm going to try to modify this. This is now M car. This is now M wheel. And then this is now the cases. This is now the cases plus the K wheel. Now, this is equal with the CSAS. This is also the CSAS. This is now becoming the X car, double dot. And this is the X wheel. This is also the X wheel.
Okay, and the second one, I have here cases. Cases multiplied going to this is X wheel. Second one is the cases plus K wheel multiplied by the, sorry, this is multiplied by X car. This is CSAS multiplied by X wheel. X dot wheel. This is the CSAS multiplied by X car. Right. Second one is cases multiplied by this is multiplied by X car. This is K plus K wheel. Multiplied by X wheel. Okay. And then this one is CSAS multiplied by X dot car. This is CSAS multiplied by X dot wheel. That is not enough. I have to add two more, which is plus and plus. This is going to be K wheel oh. This is CSAS plus K wheel. It is K wheel multiplied by X road. This is C wheel. Okay. Now, this is going to be the road. This is X road. And to make the X dot road, I need to have the derivative. Okay, and we'll case us. I will show you. I just briefly revise my model. Maybe it's correct. Maybe I made some mistake, but I'm expecting if I having some mistake, then what will happen? Okay? So you will know actually when you have a mistakes. I need to. This is still red again because the one in the workspace is not updated. So I'm going to remove everything. Okay. All right. So to, to to be quick in clearing everything, you can use the word clear all and CLC. You will clean the command window and you will clean the workspace. Okay. So I will start with mwheel, mcar first. Oh, sorry, mcar is equal to something. What do you think the mass of the car? The reasonable amount of the mass of the car? Sorry? 2,000 kilograms, say. 2,000 kilograms. But remember, this is just 1/4 of the mass of the car. That's why this is called quarter car model, because you only take one wheel, one suspension, so you don't take the mass of the whole car. So roughly take quarter, so 500. And then mass of the wheel. Any one of you change your wheel and lift your wheel? What is it? 7 kilo? 20. 20. Say 20. And then, can anyone guess the K of your suspension? How to guess the K of your suspension? You mentioned that the mass of your car is 500 kilograms. And if you ever notice that when you went into the car, if the car suspension is soft enough, you will see the suspension is slightly deflected. The distance between the tire and the over fender of your body is adjusted a little bit. So assuming that you weigh, say, 100 kilograms, say, I'm 100 kilograms. So you're weighing 100 kilograms and you went into the car and the car is actually going down, say, 1 centimeter. So 100 kilogram multiplied by G, say 1,000 Newton, and 1,000 Newton is able to deflect the suspension by 1 centimeter. But 1 centimeter is in one suspension. your whole body, that 1,000 Newton, is actually supported by 4 suspension, right? So you're able to make it go down by 1 centimeter for the 4 wheel. So 1,000 Newton should be divided by 4 wheel, which is 250. This 250 Newton making deflection of 1 centimeter. So what is the K? Get what I mean? You have, this is the original. Once you write it, it's deflected by 1 centimeter, or 10 to the power of minus 2 meters. And your load divided by 4 is 250. 2,500? Sure.
From the spring, it equal is
Exactly. So what is K?
equal the force over the deflection.
Yeah.
So the force is to
250
yes over
0.0. 0.1 or 0.01? 1 centimeter, not 10 centimeters. So 250, 225,000 Newton. So 25 kilonewton. Assuming that this is going down by 1 centimeter, which is not really the case, because normally if you driving, not everything will be going down by 1 centimeter, right? Probably one of the side is going down more, but let's use this as a simplification. So say the K suspension is 25,000. The K of the wheel normally is going to be more. You can try to calculate, but the easy one is you observe the wheel, the distance between the lip of your rim to the surface of the road. Normally it's going to be really less than 1 centimeter. I'm assuming, say, the K of the wheel is like 10 times of the K of the suspension. So if you actually loaded the same amount, probably less than 1 centimeter, maybe 1 millimeter. Really stiff wheel, 250,000. C of the suspension, there's no easy way to say this, but you can actually predict. If you want to, and normally every suspension is designed to tend to be more underdamped. It's normally set in the value of 0.2 to 0.5 zeta for a comfort mode. For a sports car, it's normally between 0.7 to 0.8 or 0.9. Because sports car, you like to be stiff. You don't like to drive a sports car and you're going like this. You want to be really stiff. So the misconception, if you have a lot of money and then you're trying to buy a Ferrari and you're expecting a very comfortable car, no. It happened to one of my acquaintance. He just get into the business and he become rich shortly. And one of his dream car for really so long is buying a Ferrari. Then he managed to buy a sports car, not really a Ferrari, something like that. In his mind, he's expecting driving a Ferrari is like driving a Camry, but really high speed. No, which is no. First, getting into a sports car like that is really difficult. I might not be fit in the car because getting in, unlike a normal car, you can put your leg first and then you put your butt in. In sports car, you need to put your butt first and then you put your leg in, which is not really familiar to most people. And the first time he tried the car, he started to complain. This car is very, very uncomfortable, very stiff, really not the car that he imagined. And, you know, in our place, the road is not really that smooth, a lot of potholes everywhere, a lot of bumps. So it adds to the suffer. And yeah, in less than 1 month, he started selling the car again because this is not the car that he wants. He's expecting with that amount of money, he will get really comfortable. Just not the one that you need in a sports car. Sports car is driven by a racer, and racer want to drive really fast. And racer never drive a car with a lot of potholes and bumps in the circuits, right? So normally, C of the car suspension is set for most passenger cars, set to be in the underdamped region. So 0.3 to 0.5 to 0.6. So if you have the max is 500, and the K of the suspension is about 25,000. So if you want to get it in theta equal to 0.3, the C value that we should have divided by 2 square root of mk is, you can calculate. So 25,000 multiplied by 100 square root multiplied by 2 multiplied by 0.2. What is the C value? I'm guessing it's about 1,000 or 2,000. 2,000? Okay. Let's say 2,100. Okay. CSAS is 2,100. C wheel. C wheel is really small because wheel, the tire, is more springy than actually damp. You will, if you have a wheel, a tire of your car filled with air, and you try to drop it from place higher, it will bump, right? Although it will never bump at the same place because the damping is still there. But if the damping is really high, what you have is it will not bounce. When it bounces, means you recover some of the energy. The distance between the original height and the height after it's bumping is the energy loss. So it's still going to be really, really in the underdamped region. So I'm going to say if the K of the wheel is 250,000, probably the C of the wheel is somewhere in the 10,000. Or make it even less, 1,000. Let's make the wheel more springy. So I have the CSAS, C wheel, KSAS, K wheel, M car, M wheel. Anything missing? If not, then we can try to start running it. All of this variable is already written here. Now, only the X of the road. This is now the input. See the section here in the bottom. This has representing the F. This represents the F. Okay. The F means this is the force working on the system, which is make this a force vibration, but not in the amount of force we're putting in, but the amounts of displacement. Say the amplitude. Amplitude 1 means 1 meter. You will never drive a car with a bump 1 meter tall, right? Probably really, really small. Probably 1 centimeter. So 0.01. And say this is a very wavy road, or something like, you know, the speed bump. Whenever you're close to the checkpoint, you will have a really small bump with a lot. You will have, the function of that bump is actually to wake you up, that you have something in the front, so you have a small disturbance. Not really harmful to your car, but enough to make you learn. So the frequency normally a bit high. So I'm going to put the frequency probably around 4 to 5 radian per second. So this is actually 1 centimeter, or maybe 0.5, 0.05. Okay. Seems like everything is there. I make sure no initial condition. No initial condition. No initial condition. No initial condition. Okay. And let's try to run it. Oh, I'm going to see what happened with the car body first. Okay. This is what happened to the car body. Probably I'm running it too long. I'm going to limit it to 10 seconds. This is what happened. You see this bump here? This is exactly 5 radian per second, following the frequency of the road. And oh, this is really big. Pay attention to the unit. This is in meter. So this is about 4 to 5, slightly less than 5 times 10 in the power of -4 meter. So 10 in the power of -4 meter is what? 0.5 milli, 0.5 milli. And what happened in the beginning? What do you think happened? Why in the beginning there's something weird?
Yes. Or 0.1 meter.
Yes. Yes.
It's very hard, or like this.
It's like very small. You can feel it, because the one that you feel is not the displacement. The one that you feel is the acceleration. Do you feel the motion of the Earth right now? We're actually spinning probably in 10,000 kilometers per hour. The Earth is spinning. Do you feel anything? Why? We're moving really fast right now. Because, alhamdulillah, the Earth is spinning at acceleration all equal to 0. Imagine if the Earth is spinning, suddenly it stops. All of us probably will be. Actually, it's not the position, or it's not the velocity that kills. If you drive your car really fast, it's not the speeds that kills you. It's sudden acceleration or deceleration that kills you. Driving really fast, 100 kilometers per hour, suddenly there is a wall. Wow. So 100 kilometers per hour, suddenly stop. That acceleration kills you, not the speed. You will be fine driving in 100 kilometers per hour, as long as you're driving constant, or even if you have deceleration, you will decelerate slowly. Drive 100 kilometers per hour, suddenly the driver press the brake. All of you will fly to the. So you can feel it. Maybe if the acceleration is enough, probably you can feel it. But my question: what happened in the beginning? Is it simulation error? We don't have initial conditions. All initial condition already set to 0. This is 0. This is 0. It's 0. So no initial conditions, but still see something. Oh, the initial input, you mean the road? The road is constant. will check the road. Okay. This is the road. The road is constant, normal sinusoidal, nothing weird in the beginning. So what happened here? And the amplitude of this is about almost 10 times smaller than the amplitude of the input. So if you want to put it, the input here, you want to compare, the yellow is the response, the blue is the wheel. So the wheel is going to be like moving like this, and you inside the car probably moving like this. Quite comfy, actually. Imagine that you have a speed bump, but you don't really feel that much shaking. But my question is, what happened in this very beginning? We're talking about this again and again. What happened here? Any guess? Any other answer? Remember, what classification is this? Free vibration or forced vibration? If this is free vibration, if I don't put any initial condition, there will be nothing happen. But I put all initial condition equal to 0. But this is still a vibration. So it cannot be free, it has to be forced. But I don't have external force working directly. Yes, that's why this is now acting as a combination between X of the load combined by the K of the wheel and by the C of the wheel is the force. It's a force vibration. And in force vibration, you have two types of response, right? Transient, steady state. So even though you don't have initial conditions, the initiation of the force, in this case by X from the road and K from the wheel and C from the wheel, initiate a disturbance. And that initiation of disturbance will have transient effect to the vibration system. But then that transient effect, because of the damping, will be decayed immediately. It's decayed immediately. You will not see them anymore. So after the first 1 second, you'll not see the transient response anymore. Transient response is basically gone. So here, done. After that is just the steady state response. All of the steady state response. All of the steady state response. Even though you're actually doing it in resonance, because you have significant amount of damping, you will not go to infinity. Instead, what happened is the steady state response will be decayed. And what you're going to have is just the excitation. Okay. This is one of the simple examples. This is a three-part representation, only taken is independent field. In project, I will make it more, because then you will sit in the car. Your seat is actually having suspension. Your seat itself having a hole, having a frame. Even your body in and your the whole flesh of your body having teeth. And even the whole one
having A and C to support your tag. Your goal is having A and C. So this can be extended to more degree of freedom. So depending on how detailed you want. So the question is probably what is the suspension tuning that should be done to make the person feel comfortable in the head? You know, in some cases, vibration really hits your brain. Feel pain not in the whole body, but in the head. So if you can actually model the K and E of the human body, and this is actually one of the special fields in engineering, human factor. You can actually model the whole body. You can model the whole body. You can actually model and predict the level of comfort. So if you design something and you expect that this product can be comfortable for someone, you include that parameter of the human body and you put that in the calculation, and then you can decide, okay, I will decide that this A and C should be in this bed to make it more profitable. So that's going to be the project. I'm giving you the example just for $2, but in the project, probably it's going to be $4, and you have to simulate it using. I will post that one by this week, so you can have a look, you can see. If you have any question, you can ask. Next week, I'm going to move the $2. I'm going to move to the topic of vibration instruments, which is focusing on accelerometer. Sorry, focusing on vibration instruments. Focusing on accelerometer. This is the tool. Now we're talking about math, everything, right? So what if you have an actual vibrating system? How do you know how harsh it is vibrating? You need some measures, some tool to measure it, right? So this is the tool, and I will cover discussion on how it's work, how it's actually work based on the concept. How can it measure vibration? How can we design an accelerometer, a proper accelerometer to give you good reading? Thank you very much. Oh, I haven't taken the attendance. Can somebody write the attendance? Thank you very much. I hope this recording is good. If I have this recording, I will share it. All right. Thank you very much. See you next meeting.